Thank you so much, Claudio, for the very kind introduction, and thank you so much for the organizer for inviting me. So as you heard, I'm going to talk about Sparks, or Succinct Parallelizable Arguments of Knowledge. And this is a joint work with Nomi, Cody, and Ilan. So before talking about Sparks, let me start by just telling you a little bit about just succinct arguments of knowledge, or even just succinct arguments. So as you probably all know, succinct arguments are one, or at least what I think, are one of the central contributions of computer science to blockchains, but also to just the world and philosophy in general. It's just such a fascinating concept. It's a concept that originated with the notion of interactive proof, defined by Golos and Merkle and Rakov, continued through the notion of probabilistically checkable proof, PCPs, and the final notion of succinct argument was formalized by Killian and Merkle in the early 90s. So what is a succinct argument? So let's say I would like to prove to you that a statement X is true. So to formalize this, we consider some statement X in some language that is an NP. And it's very easy for me to prove that this statement is true by just giving you the witness, and then you can look at the witness and check that this statement indeed is true. But sometimes checking that the statement is true, even if you have the witness, could actually take a pretty long time. So the succinct argument, what we want is to have a prover convinced to verify that the statement is true, but doing so much more efficiently than the time it takes to just verify the validity. So to formalize this, we have a prover P that takes the statement X and witness as input, and a verifier V. And what we require here are a few standard properties. The first one is completeness, which is that if X indeed is true, then the verifier should accept. Soundness says that if X isn't true, in that case, the verifier should not accept. So to formalize this, what we actually say is that no probabilistic polynomial time cheating prover can convince the verifier. Often we'll also consider a slightly stronger notion of soundness, which is called an argument of knowledge property. And this property says that if the prover manages to convince the verifier, then not only the statement should be true, but the prover actually has a witness, knows a witness to the statement. Now, the crucial novel aspect in a succinct argument is the efficiency property. And that property says that the verifier should run very fast. In particular, it should run in time poly log t, where t is the time needed to verify the statement. Now, since the verifier runs in polylogarithmic time, that directly also implies that the communication complexity is also very small, i.e. succinct. So the communication is also going to be polylogarithmic in t. So this is all great. What we're going to focus on today is the overhead needed from the prover in order to complete this proof. And the standard definition in a succinct argument just says that the prover's running time should be polynomial in t. So from a theoretical point of view, that means that prover is efficient. It runs in polynomial time in the time t needed to verify the statement. So that's great. But if you actually want to implement these things, that overhead in the prover complexity could actually be pretty prohibitive. In particular, let's look at probably the most famous example for succinct arguments, which is that of secure delegation, or secure outsourcing of computation. So let's say I have this little laptop, that's my laptop, and I would like to delegate the computation of some very expensive program M to the cloud. So I provide the program M and some input to the cloud, to AWS. AWS performs this computation for me. And let's say this is a computation that takes a pretty long time. How can I know that the answer to the computation that AWS provided is correct? So through a succinct argument, I could simply ask the cloud to also provide a proof that indeed y is the output of this program input x. Okay, so this leads to this very elegant compute then proof paradigm. So I give the program to the cloud computes the program, and then provides a proof that indeed the output is correct, and then I don't have to trust the cloud anymore. Okay. So in order for this proof to be meaningful to me, having a small laptop, we require this proof to be succinct. It should be basically independent of the running time of the program, because if the proof is huge, then of course, even just reading it, I could have just computed myself. Now, in order for this application to make sense in real life, it's important that AWS overhead here isn't too high in computing proof. For instance, if the proof overhead is, let's say, t squared, then it turns out that this whole paradigm that looks so great becomes useless in practice, because a computation that would just on its own take 1 hour will now take 4 million years to compute the proof of. So in order for this paradigm to make sense, in practice, we really require that the running time of the prover to be pretty small, also pretty close to the time t. Let me also point out, since this is a blockchain workshop, these type of delegation applications are very important in lots of different blockchain applications, starting with applications in Zcash for getting privacy-preserving cryptocurrencies, and now more recently to just prove the correctness of various different smart contracts. So if the smart contract takes a pretty long time to evaluate, it would be ideal to just post the answer to some long computation on the blockchain and a proof that it was done, and then nobody has to recompute this whole smart contract, but can just check the succinct proof of the validity of this computation. All right, so what is the state of the art in terms of prover efficiency? Because that's going to be the focus of this talk. So it turns out that actually, from a theoretical point of view, it's basically solved the question. It turns out that we have these solutions that are quasi-optimal, meaning that the prover's running time is t times polylog t. So t would be completely optimal, right? T is the time needed to compute this program. And so here we just have an overhead that's multiplicative of polylog t. And in fact, this follows quite easily by relying on the most state-of-the-art constructions of PCPs. I won't go into detail on what PCPs are, but it really won't be necessary for the remainder of the talk. And combining that with Kilian's original approach to getting succinct arguments. So that looks pretty great. But sometimes even this polylog t overhead is pretty prohibitive. And if we'd like to minimize this, and indeed in recent years there has been a flood of work trying to get down this polylog to be as small as possible. And so there are so many works, it's not even, I can't even put them on one slide. It's really in this last decade an abundance of work trying to shave down polylog factors and shaving down constants to making this overhead as small as possible. But if we're going to rely on this approach, which is indeed what most of the works in the literature do, a major open problem on even just with PCPs is to get PCPs with just constant overhead is still unknown. Thus, PCPs require logarithmic overhead. So it seems that we kind of hit a wall here. There's a lot of work trying to improve, and these are very, very important works, and we'll get back to why even shaving off constant or log factors here is important. But his whole general paradigm seems to be stuck even at seems very hard to get something which is constant overhead. Now, I would argue that sometimes even just a factor 2 overhead is too much. Right? And at the moment I'm saying we don't even know how to get a constant overhead, but even 2t is sometimes too much. And so the question is, can we get something this good, even just a factor 2 or even better? Okay, now I'll get back to why sometimes even 2t is too much. And indeed, there has been this very nice approach relying on something called parallelizable PCPs that shows that actually you can get just basically t plus some polylog t overhead. So not even factor 2, just some slightly small overhead if you have a lot of parallelism. So in particular, this very nice work by Benson et al. From 2013 showed that if I give you t parallel processors to the prover, so if the prover has lots and lots of parallel processors, indeed it can actually compute this proof basically in with just a small polylogarithmic overhead, additive overhead. So note here it's t plus polylog t as opposed to t times polylog t. But the problem with this approach is that now you require lots and lots and lots of parallel processors. So you require as much parallelism as the running time of the computation. And I won't go into detail on this, but it relies on this notion of a parallelizer PCP, a PCP that can be computed where each bit of the PCP can be computed in small parallel time. All right, so summarizing the state of the art, before I do that, let me just mention that I'm currently here, and throughout the whole presentation, I'm going to ignore the security parameter in all these expressions. So actually, when I write t times polylog t, it's actually t times polylog t times security parameter, or some polynomial security parameter. So t, I consider that as being something that's pretty big. I think of that as some large time, and we're considering proofs that are independent of that want to be essentially independent of the running time, but they will depend on security parameter. All right, so summarizing the state of the art, and again, I'm ignoring security parameters here. The original succinct arguments, they relied on a few parallel processors. In fact, one was enough. But they had some arbitrary polynomial overhead in terms of prover running time. The later ones, and all the more modern ones starting from 2005, they have quasi-linear complexity. So that means that the prover's running time is t times polylog t. And then this approach from the 2013 paper shows that actually you can basically have no overhead in running time, but at the price of using a linear number of parallel processors. So obviously, the open problem here is to get something that is in this regime, and that's going to be what we call Sparks. So Sparks are succinct arguments that have basically no overhead in terms of running time and use a small number of parallel processors. So let me now formalize this notion. So the key idea behind Sparks here will be to compute the proof in parallel to the computation. So think of this running example of outsourcing something to AWS, to the cloud. You send the program, the cloud is going to compute the program, and at the same time that it's computed and program, in parallel, actually compute the proof. Right? So in a little bit more detail, it's going to be a succinct argument where the prover computes both the program here and the proof using time t plus polylog t. All right, note that it's actually, to achieve this, it's not going to be okay to first compute the program and then compute a proof based on just the answer, because if you just have the answer, you need to have some extra kind of information to compute the proof. So it's going to be crucial that we actually compute the program and at the same time compute the proof. And now, in contrast to this 2013 paper, is we're going to only allow you to have polylog t processors, parallel processors. So there will be some overhead in the prover. And in terms of total work, we're actually not beating the previous work. It's still going to be t times polylog t total work. But what we have done here is we pushed all the extra work into parallelism. So the running time is still essentially just t, but all the extra work is pushed into parallelism. Okay. Any questions on this notion? All right, so a little bit more formally, it turns out that even to define this notion, you have to be a little bit careful, because as we said, in order to achieve this, it's important that the computation is done in parallel with the proof. So if we want to formalize this as an empty statement that we're going to prove, we have a program M, an input X, some running time T, and some output Y. And we have some witness W that certifies that this program M on input X outputs Y. Now, typically, when we define interactive proofs, we're giving the prover and the verifier the whole statement that we want to prove. But here, what we want is for the prover to compute the program and at the same time the proof. So we're actually going to consider a scenario where the prover doesn't get the whole statement, in particular, doesn't get Y. But instead, the prover only gets mxt and needs to compute Y and convince the verifier of this, and at the same time send Y to the verifier. So it's kind of, we have this delayed output, so Y is not known in advance. P and V only receive M, X, and T as inputs. And this is because we have this super tight requirement that we want you to, even just a factor 2 is too much. So computing it first and then computing the proof, that would already give you a factor 2 overhead. And so we don't want that. That's why we say, I'm only giving you M, X, and T, not the output. You compute it, and at the same time, give me the proof. Okay, I'm not going to go over these things very formally, but the completeness and soundness properties are basically as before. So completeness says that on input M, X, and T, the verifier eventually is going to output the output of the program Y. And the soundness property, we're going to formulate as an argument of knowledge property, saying that if indeed V outputs Y, then P must know a witness W such that this statement is true. And efficiency, as we said before, the prover runs in parallel time T plus polylog T using polylog T processors. And again, I'm ignoring here the security parameters. Actually, we have an extra security parameter here. And as before, as the standard properties of succinct arguments, the verifier's running time should be polylog T, and the communication therefore is polylog T. Is this all clear? All right, so now I've introduced this notion of a succinct or a Spark, a succinct parallelizable argument of knowledge. Now the question is, what can we achieve? And our main result is that assuming the existence of collision resistant hash functions, there exists a 4-run Spark for all of NP. So we can actually prove all of NP with essentially no overhead in prover running time. And the only overhead has been pushed into parallelism. We can also prove a non-interactive version of this. So if we assume the existence of collisions in hash functions and a so-called quasi-linear Snark, I'll get back to that, come back to what that is shortly. There exists a non-interactive Spark. Let me just mention that all standard or all state-of-the-art Snarks satisfy this quasi-linear efficiency property, and therefore we can get non-interactive Sparks based on the same assumptions as we have Snarks today. And the way both of these two results are proven is actually through a general transformation. And the way this transformation works is we start off with any succinct argument that satisfies this quasi-linear efficiency property. So quasi-linear efficiency just means that the prover efficiency is T times polylog T. So if you recall that statement of our picture, the Actually, let me get back to the picture. This is these all more recent works, the work starting from 2005, have causal linear proof efficiency. So start off with any one of these most recent succinct arguments and plug them into our transformation, and what you get out will be a spark. Okay. So one way to think about this transformation is what we're showing is a method for trading off time for many processors. So these previous works had time t times polylog t. So the total work is t times polylog t. We will have the same amount of total work, or actually a little bit more even, but asymptotically it's t times polylog t. But the running time is going to be essentially t. So the time is t, but all that extra work has now been pushed into parallelism. So in particular, if you plug in Kilian's arguments with the Benson-Sudan PCP, we get a spark, the forehand. And if we instead start with a causal linear snark, we're going to get non-interactive sparks. So the focus of my talk will just actually going to be on this interactive setting. I'm not going to talk much about these ones, and I'm going to try to show you how to get a causal linear succinct argument and turn it into a spark. Okay. But before doing that, let me briefly mention some applications of sparks. I mentioned in some applications, even a factor 2 overhead improve efficiency is too much. So let's see how we can use sparks in such applications. So the first application is actually the original running example I had, which is delegation. So in the case of delegation, let's say that you're outsourcing some complicated computation that you're doing some drug discovery, let's say, and you have some competitors. They're also doing their own drug discovery. Now, if you just don't want to buy all the computers, you prefer to outsource this computation to a cloud, because potentially for AWS, computing power is actually a lot cheaper because they have economies of scale and so on and so forth. Now, if this computation, let's say, takes 2 years to run, and then computing the proof has an overhead of a factor 10, even just a factor 10, then now suddenly that's something that's going to require 20 years to get back the proof of. Now it becomes useless for you, right? Because your competitors maybe are willing to buy the computing power and just run it on their own, and now you lost all your the advantage you have. So even in the case of just outsourcing computation, it turns out that even a factor 2 overhead could be too much. However, with a spark, we can now just send m of x, m and x to the cloud. The cloud computes m of x equals y, so it gives back y to you, and at the same time computes this spark, and you get back the answer within time t plus polylog t. So if you have access to a spark, you can now get delegation with optimal approver runtime. Now, again, of course, AWS will have some overhead in terms of parallelism, but they have lots of computers anyway. So you might have to pay a higher price because to get the proof, but maybe that trade-off in prices anyway. Maybe it would have been even more expensive for you to actually set up this infrastructure in-house. So maybe you're willing to pay an extra premium in terms of the price, but you're not willing to pay a premium in terms of running time. So as a corollary, what we get is directly assuming collision-resistant hash functions and a causal linear snark, you can get a time-type delegation scheme where this is just a single message. And if you're willing to go for interaction, which is fine, just CRH suffice. Another application is to so-called verifiable delay functions, or VDFs. This is a fascinating concept that was introduced a few years ago by Bonnet et al. And has had lots of awesome applications to blockchains. So to define this notion, let me first recall the notion of a sequential function. So a sequential function is a function, or a t-sequential function, is roughly speaking a function that can be computed in time t, but it can actually not be sped up. So it cannot be computed in time t times 1 minus epsilon t. So t times 1 minus epsilon. Right? So it's something that takes a long time to compute, but it can actually not be sped up. There are no shortcuts. So the canonical example of this is repeated squaring, modulo composite, and unless you know the factorization. So sequential functions are great. These are so-called delay functions. But an issue with a sequential function is that if you have computed it, nobody can actually check that the answer is correct. Right? The only way to check the answer is correct is to recompute it, which takes a long time. The notion of verifiable delay function overcomes this second obstacle. Roughly speaking, a VDF is a sequential function that additionally contains a proof of the output, of the correctness of the output. So once you compute it, you not only manage to compute the output, but you also have computed a proof that the output is correct. So at first you might think, look, VDFs are trivial. Just take a sequential function and combine it with a succinct non-interactive argument, a Snark, right? And just apply your sequential function and then combine it with your proof. The problem with this is if the proof has some overhead, then when you combine these two things, it actually takes a lot longer to compute the function and the proof. And now an attacker, however, might actually come up with a, compute the output much faster by simply ignoring the proof. However, if we have a Spark, then this naive transformation actually works. You can just take a sequential function, combine it with a non-interactive Spark, and that directly gives you a VDF, because there's no, you can actually, with a Spark allows you to compute this and the proof in time, just time t. So that gives you directly a VDF, and the proof of this is in the paper. So let me mention that the previous general construction of VDFs, there are now lots of very nice constructions of VDFs based on concrete assumptions. But if you want something based on general assumptions, the best previous construction started off with something called an iterated sequential function. So an iterated sequential function is something like repeated squaring. It's a function that you keep iterating. And we're assuming that the iteration of this function cannot be shortcut. That's one way, one type of candidate construction of a sequential function, but not all sequential functions necessarily have this iterated nature. So previously, starting with iterated sequential functions and Snarks, one could get VDFs, but we can now start off with any sequential function. And this actually has an important advantage, because some sequential functions actually are not iterated by design. There are these so-called memory hard sequential functions. And these are sequential functions that not only require some running time, but require to also have a lot of memory. Turns out that actually our transformation doesn't really care at all about any properties of sequential function. If the sequential function is memory hard, then actually what we get after our transformation is going to be a memory hard sequential function that is verifiable also. So using a Spark and starting off with some general sequential functions, or for instance, a memory hard sequential function. And indeed, in fact, in recent years, there's also been an explosion of works trying to study various different memory hard sequential functions. It turns out that there are many many subtleties in even how to define memory hardness. I'll refer you to the paper where we actually don't discuss in so much detail, but we reference some of these early recent works that discuss some of the subtleties in defined memory hardness. There are lots of different very nice notions on this, and some very recent nice constructions. So take any of those candidate constructions of sequential or memory hard sequential functions, combine it with a Spark, and you now get a candidate construction of memory hard verifiable Delane function. And let me point out that VDS have had a lot of very nice applications to blockchains, and there have been these suggested recent applications of using also these memory hard functions in order to get more ASIC resistance. So by using the Sparks, one could get these memory hard VDFs, and you can kind of get the best of both worlds. And so, as far as I know, well, because before this work, we didn't have any candidate constructions on memory hard VDFs. There haven't been any applications of this formalized, but I will leave that to future work. All right, so for the remainder of the talk, I'm planning to give you a very brief overview of this construction of a quasi-linear, of how we can take a succinct argument and turn it into a Spark, assuming the existence of collision-resistant hash functions. And for now, I'm going to make a bunch of simplifying assumptions. The first one is that we're going to assume, for simplicity, that actually we have access to a non-interactive succinct argument of knowledge. And additionally, I'm going to assume that original program that the proof is proving something about is a sequential RAM computation. So the original program M is a sequential algorithm. It's not a parallel algorithm. Okay. And as a warm-up, let's actually consider an even more simplified scenario. And that's a scenario where we have a program that uses a very small amount of space. Okay. And this idea actually originated or is implicit in some very nice works from a few years ago on VDFs. And here in this warm-up, we're going to show how to use this idea to get Sparks for small space computations. Okay. So remember, in a Spark, we need to compute some program M on input X and some witness W, producing some output Y. And at the same time, we need to produce this proof. Okay. So let's again make another simplifying assumption. Let's assume that we don't have a Snark with quasi-linear efficiency, but in fact we have something that's pretty great that has a factor 2 extra overhead. So the proof just, so this computing this takes time t, and computing the proof takes time t. Okay. As far as I know, we don't know how to do this even for very simple computations, but let's assume we have this for now. And let's see how we can use this in order to get a Spark. So the proof takes as long to compute as the actual computation. All right, so since, remember, we need to complete within t steps, both the computation and the proof. So what can we do? Well, basically start running a program. After t over 2 steps, stop it, and then start computing the proof. That's going to now complete after t steps. So now what we have is a way to compute in time t a proof of correctness of the computation after t over 2 steps. So that's not great because we need to look at the output after t steps, but at least we've made some progress. We say, okay, after t steps, we can at least compute something about the memory content of the computation after t over 2 steps. Okay, but now once I'm computing this proof, why don't I start continuing running the program? So just recursively compute and prove the rest in parallel. So what do I mean by this? While you compute this proof, which is a proof about this thing, continue running the program. You have parallelism, right? So continue running the program for t over 4 steps and provide a proof of those t over 4 steps. And then once you've done that, continue running it for t over 8 steps, compute the proof, and so on and so forth, and eventually get something that's so small that you can just verify by hand. So what happened here? Well, it turns out that you only need log t of these threads and this log t of these proofs to actually provide the proof for the whole computation. So now we do have a log t increase for prover and verifier in communication complexity, but this overhead is all done in parallel, and in fact the running time is just t. Furthermore, there was actually nothing magical about this number 2 here. If the proof had a factor 10 overhead, then we could have just started off by computing t over 10 steps and let the proof be computed, and we could have just done the same thing, and that would have still actually given you roughly, actually we're given 10 log t parallel threads. And more generally, if the overhead is 8 times t, then you're still going to get roughly 8 times log t parallel threads, and this gives you something that only has now polylog t overhead in parallelism. All right, so this is was a very simple approach when the amount of space is small, but the problem here is, what are we actually proving here? What is this a proof? Well, what I'm proving here is starting the program from this point and going to this point. And what does a point mean? A point means a certain memory configuration. So going from this 0 memory configuration to some memory configuration here, I'm proving that is correct. And then here I'm proving that starting from that memory configuration, running for t over 4 steps leads me to this memory configuration. So if you look at these proofs, they actually grow with the size of the memory. So really what we're proving here is some starting points configuration leads to some end configuration within t steps. And if you just do this naively, the statement and therefore the complexity of this proof grows with the size of the statement, and that is the space of the computation. So when you have computations that use a lot of space, this just doesn't work. So the naive attempt here would be to, okay, why prove something about the whole memory? We know we should use hash functions. Let's just hash down the space and let the prover prove that, in fact, the statement now is going to be, here's a hash down state, here's another hash down state, taking k steps takes me from this hash to this hash, from this digest to this digest. Now the statement is small. The problem here is if you look at the witness to this is actually the whole memory. So the witness is still big. So this approach actually doesn't quite work either. Okay. So what we're going to rely on is the idea here that actually, if we use a nice hash function, in particular a Merkle tree hash function, as is well known, these Merkle tree hashes have this nice property that they're updatable. I can give you a short certificate that I have just done a certain number of updates into the memory, and the updates, the size of the updates are just grows polylogarithmically with the size of the database. Okay. So in essence, we're going to use the same approach with digest 1 to digest 2, or start to final. And the prover is going to prove that we've done a certain number of updates into memory, k updates if you're running program for k steps. And these updates, they are verifiable. So this is just, it's a memory access and a proof, an authentication path that shows you that in fact I did only get minor change, this particular one change into the memory. So now that seems very easy. Why don't I just provide this proof? This proof now only grows with the number of updates. So it's so the witness is short, the statement is short, all great. The problem here is, how do I compute all these updates at the same time as the computation? Right, so that is now the main obstacle, that I need to be able to update this Merkle tree in parallel with the computation. And if you look at how updates are done in a Merkle tree naively, they actually require doing log and sequential steps. So it seems like we're kind of dead already. However, what we'll show is that actually we can, in essence, pipeline these updates to the Merkle tree and do them all in this pipeline parallel fashion. So even though it actually is going to take log and steps, the log is only going to be something additive towards the end. So many of these steps can be done kind of in a pipeline fashion. So they do take log and time, but it's done pipelined. So eventually you're going to only get an additive overhead of log. So I'm kind of running out of time. So let me go over this kind of fast and on a very high level. So recall in a Merkle tree, we have some database to hash it down. I'm going to take 2 elements here, hash those, and eventually I get the root here in the digest. Whenever I would like to make an update to a position, let's say here, then I'm going to present you with the root, with the path from this position down to the root, as well as this authentication path, which are the siblings of all the elements that I'm touching. So to certify that this thing has been updated correctly, I'm also providing you with a sibling and so on and so forth. Okay. I assume many of you actually seen this Merkle trees and how Merkle trees can be updated locally. So I'm admittedly doing this very fast. Now, so let's say I'm updating this position. I need to present you with this and also all these reds. These are these authentication nodes, leaves that allows you to check that indeed I'm updating this digest correctly. So here is the key observation, which turns out to actually be a very simple observation. It's almost surprising it wasn't made before. So it turns out that Merkle trees are amazing. They are actually what we refer to as concurrently updatable. They're not just updatable, but they're also concurrently updatable. So that means that I can actually do many updates to them with essentially no multiplicative overhead in terms of running time. So let's say I would like to make a write operation here. So I'm going to do some updates to this. I need to also read this in order to compute this node here. So I do that. That's in position in step 1. Then in step 2, I need to read this extra thing here in order to update the next nodes, the ancestors. At the same time that I'm doing this, that I'm doing the second step here, I can start accessing something else and start working on that and start hashing these 2 things to get that. Okay. When I do that, I can now go back and do the third thing. And the third thing can actually be the same one as here. And the key point here is that when I'm reading these 2 things, the updates that I'm doing for things that happened here before, they're already kind of higher up in the wave. So all these updates, you can think of them as little waves coming. And even if I start updating something behind here, that wave is never going to catch up to this one. So that's why there will be no interference, and I can actually do all these things in parallel. And it's only the last final update that will require some extra log and steps. So the conclusion here, with this Merkle trees, you can actually compute these K updates in parallel with the whole computation. And in a paper, we formalize this as a property, as a new primitive called a concurrently updatable hash tree. And let's now see how we can use this on a high level, these concurrently updatable hash trees or Merkle trees with concurrent updates to get a spark. All right, so we'd like to get a spark for some computation takes time t. So we start by initializing an empty database and gets the digest 0. Then we're going to do some K1 steps of computation. And in parallel to those steps of computation, we're going to actually compute these updates to the Merkle tree. And remember, they can be done in this like parallel fashion with these waves, they're not touching each other. There will be some extra time spent here, things hang out for the final operations. That's some extra log t time. Once we have computed this thing, we can now provide a proof that this digest created the digest at the end of this using these updates. That's the new witness for the proof, and that has some overhead. Let's say factor 2. Okay. In parallel, at this point when this is done, we can now start doing some other K2 steps and some other updates. And once those updates are done, we can provide a proof, and so on and so forth. And if you continue in this fashion, it turns out that if the overhead, if you start off with a quasi-linear Snark or succinct argument, then you will only need M, which is polylog T parallel threads. And this will all complete in time T plus this extra little overhang, which is polylog T.
Rafael, we are running out of time.
Okay, so I will quickly wrap up here. So, so to conclude, all of this finishes in parallel time T plus polylog T, and the Spark complexity is M times the complexity of the underlying Snark. So there is some extra overhead in terms of parallelism from the underlying Snark, but it's only polylog T. Proving the security of this thing turns out to actually be a little bit tricky. I won't go into detail on that. The issue here is that we have lots of different Snarks that all have lots of these arguments of knowledge. You need to run with arguments of knowledge extractor from each one of them. Since you're running many of them in parallel, this leads to problems with the composition. It is dealt with in the paper. This actually requires coming up with some new definitions of proofs of knowledge that compose nicely, that I think are of independent interest. I won't really go into the detail on the interactive case now because I'm running out of time. When it's interactive, if you do things naively, you can also get a blow up in terms of number of rounds in the protocol. However, if you rely on some specific instantiations of interactive succinct arguments, you can actually sync up message in a clever way in order to get this forehand protocol. I won't go into detail. So to summarize, Sparks are these what we think of as a new parallel, where we're computing the proof not after the computation, but in fact in parallel with computation, and that allows us to get proofs that can be computed together with the actual computation with just some very small additive overhead. However, we do need polylogarithmic many processors. So far, everything I told you about here only dealt with sequential programs M. Ideally, we would of course also like to deal with programs M that already use parallelism. Right? When I want to outsource a computation to Amazon, most computations today actually severely leverage parallelism. And so if you use the approach that I just showed you here, that requires first transforming your program to a sequential program and then providing a proof Spark for that. And that already would impose huge overhead. In the actual paper, we do deal with also Sparks for Pramps. So again, I won't go into detail, but what we can achieve is if you already use P parallel processors, I'm going to be able to do the computation in the same time T plus polylog TP. TP is the total amount of work, T is the time, P is the number of processors, using P times polylog T processors. So again, as before, we have an overhead now of polylog T in terms of number of processors, but we're preserving the time. All right, details are in the paper. So to conclude, we introduced this notion of a Spark that allows you to compute and prove any statement in MP, in fact, any non-deterministic PRAM in time T plus polylog T, with just an overhead of polylog T in terms of number of processors. And we did it through providing this generic transformation from succinct arguments that satisfy quasi-linear efficiency to Sparks. And we also presented some applications of these to delegation and verifiable delay functions. In particular, this gives the first construction of a memory hard VDF. I should end with this very important caveat. This is just a theoretical feasibility result. There's lots and lots of work required to make it practical. In fact, let me just briefly mention some things. So one thing this really tells us to focus on is that actually focusing on improving the constants of just succinct arguments with polynomial logarithmic overhead is crucial, because in our transformation, that overhead actually got transferred into parallelism. So if you like to minimize parallelism, we would like to really understand how much minimize the total amount of work. There are some other more theoretical problems and some other more practical. I'm running out of time here, so I'm not going to really go over them. But I think that maybe to me the key open problem from a practical point of view is to implement this paradigm and potentially implement it using some better specific updatable hash functions, maybe using some algebraic hash functions that will compose nicely with Snarks in order to get a more streamlined implementation of this. So I'll end with this. Thank you so much.